that's nice. Okay, so just for the video, I briefly repeat what we've done already on the board. So we are considering a more general problem. As compared to the previous step, we are using an arbitrary nonlinear function f, which may depend on the, I'm writing t here, and Alexander, why are you not stopping me when I'm using t here? We don't have time. We have just a coordinate x, and we have a dependence of the unknown solution and its derivative. It's possible that function f depends on the unknown solution and its derivative, and the boundary conditions at point A and point B become more general. It involves the function value and its derivative as well. So we can use the simple approach to approximate these derivatives, but this approach provides only the first order of approximation. A better approach is to use more involved stencil with 3 points instead of 2, and then we gain 1 extra order of accuracy at the boundary. And for the left boundary, the formula will be very similar. The only difference is the sign. So this is the right approximation of the derivative, and this is going to be the left approximation of the derivative. Better way to approximate this is preserving.
So for the point in our system, we should.
Thank you. Thank you. So I should have written n here, n minus 1 here, and n minus 2 here. Yes, correct. Second order accuracy. Hello, Charles. And that's it. That's all you need to solve the fifth assignment, I guess. One thing to think about for you is that this equation at the left hand side and this equation at the right hand side, they involve three values of the unknown function. And in our discussion of the tridiagonal algorithm for solving the linear systems, we can only consider the case where there were 2 terms in the equation, yes, not 3. So you need to think a little bit how to eliminate the term that you don't like from this first and the last equations. Actually, in the assignment, you will have only one condition with of this type. Only on one end, because the problem is the flow problem for the channel, and this condition, Newman condition, occurs in the center line of the channel. So you have a round channel, for example, or maybe a flat channel, like continuous in the direction that we don't draw on the board, inside the board. And we usually compute only half of the flow to save computational time. We don't consider the symmetric part of the solution because it's the same. And the typical approach is to divide our domain by half, But when we divide, we'll have to impose this kind of condition here if you use the horizontal velocity, right? Because there is no wall at the center, and there is no zero velocity condition at the center. The velocity is as it is from the solution, and this is defined by this type of condition. And here you will need this kind of approximation to preserve accuracy. Okay, with that, the theoretical part is done, and we can discuss anything you want.